Welcome to the final episode in our Radio Design 101 series. Our goal is a radio that can pick up as many stations as are out there, as many as are theoretically possible to receive. On the left-hand side, what you can see is a spectrum that goes from 88 megahertz to 108. And you can see 20-odd stations here. Some are very, very strong, and some are very, very weak. And we're going to talk about what's involved in being able to receive weak stations in the presence of these really strong ones. So in that sense, our subject is very general. We're talking about the radio arts and how to make the best receivers. But to illustrate that and bring it down to earth, we're going to look at 4 different radios. One is our homebrew radio that was covered in the Radio Design 101 series. Another one is a very modern software-defined radio called an ATS-25. This is pretty amazing. I actually bought this for this episode. In addition to that, we will review ones that we've looked at briefly before. There's a 1990 vintage portable multiband radio here, and there's a commercial wideband receiver from 2003, which is made by Yaesu. It's a VR120. And I pitted these against each other with the same antenna. This is just the lower end of the FM band, so you can see the signals a little bit more clearly. Again, there are very strong ones. This is at 96.3 FM in our area, and then very weak ones. On the right-hand side is a list of these stations, their frequency in megahertz, and their amplitude in dBm. So this super weak one on the left is about minus 96 decibels relative to a milliwatt. The new radio, the ATS-25, can kind of pick that up, but it's not really usable. So I colored it sort of a light red. All of the other stations that you can see in this plot that the spectrum analyzer was able to show, the radio could pick those up. And so they're in green. There's a tiny bit of static for these ones that are light green, but it's quite usable. Conversely, this VR120 was not able to get a lot of stations, and we're going to talk about why today. So here's our topic outline for today's episode. We're going to talk about the challenges, the engineering challenges in creating a good receiver design that can receive as many stations as are out there. That'll bring us into something called receiver architectures. So many of you know about super heterodyne receivers, and that's what we used in Radio Design 101. But there are other kinds of receivers as well that we met along the way. One is direct conversion. There are other variants like low IF and so forth. So we're going to take a look at those, and we're going to look at schematics and really go into detail there. We will then summarize some of the main points for achieving good performance in any radio design. And we'll conclude with how we are actually able to make our radio work even better than those other radios. But before we jump into all of that, I want to play you a couple of clips to let you listen to why these are colored red and the radio is not picking them up. Sometimes it actually is picking up stations that aren't there, as you'll hear. So let's begin with our brand new radio, the ATS-25. It's pretty amazing. I'm able to get most of the stations that I was able to look at on the spectrum analyzer. Turn off the mute, and we're on 87.9. There's not supposed to be anything there. Here's 88.1. There's barely something there. So it's struggling with that one. Now I'll just go on up.
Positive, encouraging K-Love.
So that one's very nice.
KGLV, Manhattan, Topeka. Showing pictures on state TV.
There's another one.
Raised hands.
Sound quality is very good on this radio. Another very good one. And it goes on like this all the way up the dial. And now the VR120, this little handheld unit right here. So it's supposed to be something on 88.1. You judge. All right, so that's 88.9. That's probably this very strong one right here. First real strong one. We're going up. $89.3, but it's not really something you can listen to too distorted. There's something else there. Nope, all distorted. Ah, that's the actual station, 89.9. So that's probably that one. We'll review this shortly. Going up a little higher. 90.3. There's two stations there. Those are actually intermods from these two strong stations, but we're tuned to here at 90.3. So with that radio, we were able to get a few stations. We got 88.9 and 89.9, but we missed a bunch along the way. Let's take a quick listen to the SW60. So first station we see is at 88, but it's actually 88.9. This is an analog dial and it's slightly off. I checked it with the other radio. This is the station at 88.9. Going up a little. There's two stations there. Let me see if I can fine tune. Okay, so that one's almost usable. Oh yeah, that one's fine. It's 89.9 FM, a reasonably strong station. And we'll just tune around further now.
Heart of
life I find.
claim that all the human race can be traced back to one.
So that old radio actually works better than the newer VR120, and we'll see why in this video. A lot of the problem deals with something called intermodulation distortion. And we can illustrate it with the signals in our area. There's one at 96.3 right here, a very big signal. There's another one at 93.3. So those are 3 megahertz apart. There's also a station at 90.3, another 3 megahertz down from this one. But it's very weak. It's minus 75 dBm. What happens is, in a radio, if you don't design it right, then these strong signals can essentially mix together and produce what's called an intermod product that can land on a frequency where a weak signal is and prevent you from getting it. So here's what that sounds like. You're going to hear 2 stations, neither is the one that we're tuned to. We're going to hear this station on top of this station at the same time.
In a tight job market with plans to consider adoption on first reading at their April 19th meeting.
So with that background, let's jump into today's topics, starting with a review of these challenges when you're trying to design a receiver. This slide summarizes what a good receiver design has to do. It's got an antenna which is trying to receive a signal. But in addition to that signal, there are other signals out there coming in which we'll call interferers. And our job is to amplify a weak signal, which could be like this little guy down here. And that's about 70 or more dB below this very strong signal, which is nearby in frequency. It's only 2 megahertz away. And before we can get this signal demodulated, we have to block out all of the other signals, because the demodulator in the radio usually is not selective at all. And so it's going to demodulate more than one signal if more than one signal gets there, as we just heard. So we have to filter out interferers. In addition to that, if we're going to receive the weakest signal possible, then we have to contend with noise. And there's noise coming into the antenna from the environment, background noise. But there's also noise being generated in the devices themselves in the radio, and we need to minimize that. In my opinion, it turns out that people spend way too much time on that because it is these strong signals, at least in some radio service bands, that matter much more than trying to receive the weakest signal possible, if you have a good antenna. Finally, you have to limit the bandwidth, generally to the bandwidth of the signal you're trying to receive. Make it just that wide and no wider, because that will minimize the amount of noise that the demodulator sees. So here is the classic super heterodyne architecture. At the bottom left, we've drawn a spectrum. Horizontal axis is frequency, vertical axis is amplitude, just like on those spectrum analyzer plots. Now, depending on your antenna, there could be lots of signals across many different frequencies that are trying to come into your receiver, and your job is to select a single one and get rid of hundreds of others. And in a classic Super Het, that starts with what we call a pre-select filter, where we select the band of interest. Say this is the FM broadcast band. And we try to get rid of this, which maybe is shortwave signals, and maybe these are nearby public safety signals that are really strong because they're nearby, and there's some other signals, etc. So we put a filter that just tries to extract these and block all these others. It doesn't do a perfect job, but we try. And then we amplify it with a hopefully low noise amplifier, and these signals get stronger. And we didn't get rid of all the other signals, but that's okay because we got another filter coming up called the image filter. And that will then filter more. And notice the noise level went up as well as the signals. This dotted line is the noise level, so it got higher as well. But before we go on to the mixer, we have this image filter which cuts down the noise outside of our passband. Then what happens is we downconvert the signal we want to a lower frequency where it's easier to filter it. And so it comes into this mixer and mixes with a local oscillator, and the spectrum that comes out of the mixer looks like this, except that it's shifted down in frequency. It moved to the left here so that now it's at a lower frequency, where it's then easier to filter. And what are we filtering here? We're generally filtering out the single channel we want. And so at the output of this filter, if all goes well, we will have the desired signal, maybe with a little noise pedestal on it, but we will have gotten rid of all of the other signals here as well as the ones up here. And then we can amplify the heck out of it and get it strong enough to feed into the demodulator, or in general, these days it might be an analog to digital converter, and then the demodulation is done digitally. So that, in a quick nutshell, is how the classic Super Het works. And if you've seen the Radio Design 101 series, then you already know that, or you may already know it from elsewhere. What we mainly did in Radio Design 101 is cover things like filters and impedance matching and the mixing operation and how we do that at a circuit level. And then in the first epilogue, we did a little bit on receiver performance to look at some mistakes that we made along the way. And some of those mistakes were circuit level mistakes, but there are also architectural issues. Maybe the Super Het, as shown previously, is not exactly the right thing to be using. And we're going to talk about that in this video. Because we have this problem that the signal environment is harsh. We've got these really strong signals and very weak signals that we're trying to receive in the midst of the strong ones. And in our design, we had a front-end gain of about 20 dB in the LNA, and the filtering that was before and after the LNA was fixed tuned. In fact, it peaked at around 98 megahertz. So the output of the low noise amplifier filter combination, which we call the front end, is the input spectrum where all the center stuff is amplified. The other stuff is amplified also, but not quite as much, and the result is over here. The problem was that this signal that was very strong went really strong after it was amplified. And it was too strong, and it hit this mixer with about 20 dB more power than the mixer could withstand. The 1 dB compression point of the mixer was minus 20 dBm, and we were hitting it with close to 0 dBm. And that resulted in a lowering of the overall gain in our receiver. In addition to that, as we're going to see in this video, that can create these intermod products. And lastly, we had kind of a single filter, so we had limited off-channel rejection. I think that might be one of the issues in the VR120, as we'll see. We're going to look at some schematics. So there are two basic problems that these strong signals will create for us. One is called the blocking problem, and the other the intermod problem. Let's take them one at a time. The blocking problem is illustrated here. Now, this isn't for our radio. This is just general material. This is true for any receiver. Only the numbers vary. The problem is this. Coming into the antenna, you may have a desired signal which is very weak, and I made it very weak here, minus 110 dBm. And you may have an interferer which is very strong, even stronger than I showed you. Maybe you got one at minus 10 dBm. F1 is our interferer frequency, frequency 1, and F0 is our desired frequency. Now, we're going to run those through a filter, and ideally the filter would get rid of F1, but as we learned in Radio Design 101, that could require a quality factor on our filter which is much higher than we can do in practice. And so in general, the front end of these receivers often lets many signals through. And let's say these two are close enough together that we could not filter out F1. So what happens? Well, we go through an amplifier. In this case, it's 30 dB gain. And what we would expect to happen is the minus 10 dBm interferer would increase by 30 dB and go to plus 20 dBm. Now, what's the problem with that? Well, plus 20 dBm is 100 milliwatts. And that would require an amplifier that burns at least 100 milliwatts, if not a watt of power. So we're probably not burning that much power in our LNA because we got a battery-powered radio. And so what happens is the output clips. And the actual output at frequency F1 is now here, somewhere around maybe 0 dBm. So it's depressed by about 20 dB. Meanwhile, the desired signal at F0 at minus 110 dBm at the antenna should have gone to what? Minus 80. But it didn't get there because we've already depressed the gain in this amplifier. So when the output signal clipped at F1, it also lowered the gain. And so maybe it comes out at minus 95 or something like that. But notice the noise level. The noise went up still almost 30 dB. And so now this actual output power from the desired signal is below the noise floor, and we don't receive it. So that's summarized here in the effects column. What are the solutions? What could we do? Well, we could burn a watt or more in the LNA if we're not battery powered. Or we could decrease, and we should decrease, the LNA gain. You probably shouldn't have a 30 dB gain in the LNA. 10 or 20 dB is typical. And finally, we could try to filter out F1, but for reasons I just mentioned, maybe that's hard or not possible. Well, no, in this video, we're going to look at a way that we might be able to do that at the end of this video. And lastly, I want to stress that this slide is centered around the LNA, but these effects occur in the mixer too. And in fact, in our design and in most designs, it's the mixer that's going to see these problems before the LNA does. The other problem is the intermod problem. And in most cases, this is the hardest problem to solve because it can occur with not really super strong signals, but with moderately strong signals like minus 40 dBm. And I think this is at the root of the problems that we experienced with the VR120. Now we have the desired signal, again at F0, minus 110 dBm, but we have two interferers at F1 and F2. Notice that the spacing between F1 and F2 is the same as the spacing from F1 to F0. That's important because when we amplify all of this, these two strong interferers will get amplified. They're not going to saturate because they're only at minus 40 dBm. But due to some interesting features of what are called nonlinearities in the mathematics of the way these amplifiers work, what happens is you get a mixing operation essentially. These two frequencies can mix together and produce new frequencies. One is here to the left and one is to the right of the pair. And the actual values are shown up here in the top right of this slide. If one of these happens to fall on the frequency you're trying to receive, the intermod product here maybe is at minus 70 dBm, and our desired signal, well, it was amplified up from minus 110 to minus 80, but now we got this new signal that's been generated, and it's bigger. And so it's going to basically prevent you from receiving the signal you want. And we heard this. We heard it when we tried to receive a signal at 90.3 FM, but we had two strong interferers, one at 93.3 FM and one at 96.3, 3 megahertz apart, and they mixed down, and we didn't hear the desired signal. We only heard these two. Now, the solutions here are the same. We could burn more power. It's one of the reasons spectrum analyzers are able to show signals that sometimes you can't receive with your low power receiver. Spectrum analyzers, the one I was using there, plugs into the wall and probably burns 100 watts or more total. They also don't have a low noise amplifier in them usually, so they're kind of deaf. But here we have a low noise amplifier and we had too much gain. We could improve this problem by backing off this gain to 10 or 20 dB. That would probably solve it here. And the good radios, including that new ATS-25, actually does that. It has automatic gain control where it backs off the gain when it sees that the signal coming out is too strong. And finally, filter out F1 and F2. Again, these are probably too close to here for normal filter technology, but we're going to use something called Q-enhanced filter technology, which is based on an old technique called regenerative gain. And we're going to be able to do this. So we're going to filter out F1 and F2, or at least decrease the signal levels there so that we can solve the problem. Now, radio designers have known about these challenges for decades, and they do the best they can. One of the things they look at are alternatives to the Super Het receiver with the fixed tune filters at the front end. Over the years, there have been other radio designs as well. Even before the Super Het, there were things like tuned RF receivers and these regenerative receivers. So we're going to look briefly at those, but we're going to spend most of our time on super heterodyne receivers and more modern direct conversion receivers. Now, this slide and the material coming up, the diagrams that I'm going to show you, come from a document that I wrote long ago, back in 1995. And if you want to actually do some reading rather than just listen to this video, then you could just search for this online and you'll be able to pull it up and read through it. This is chapter 4, and it's only a couple dozen pages here. But I'm going to talk through them real quick. The other thing I might mention is as you're watching this video, we're several minutes in at this point, if not more, and you can pause it. And I would encourage you to do that. There's a lot of material here to absorb. And I wanted to pack it all into this final episode, but, do yourself a favor, pause it here or pause it wherever and study things, go take a break and come back to it. All right, let's look at some of the architectures that have been done in the past. The first one was this tuned RF receiver architecture. And crystal radios were like this. They had a bandpass filter right after the antenna and then a detector. But then after vacuum tubes came in, they figured they could amplify it as well, and that got them to be able to receive weaker signals. The problem with this architecture is that the bandpass filter, especially if you're doing it right at the radio frequency coming in, is extremely difficult to do and impractical in today's dense spectral environment. Knowing that, some clever people long ago figured out they could do something called a regenerative receiver. It's basically the same thing, except they took a little bit of the amplified signal and fed it back. According to the math, what that did is it made the filter more narrow band, and so it could filter out the interferers better. They used a single tube here, and again, the filters were hard to do, but you put this together and they work quite well. And there was also one called a super regenerative receiver architecture. I'm not going to go into that. The only place I know it was ever used in my lifetime was like a garage door opener in the past. So here's a neat example of a modern regenerative receiver. This is really kind of a hobby kind of thing. It basically goes from 3.5-ish megahertz up to 22 megahertz in 5 or so bands. And when you're receiving, what you do is you tune to the frequency or near the frequency, and then you turn this knob up and it amplifies better, and it also sharpens the filter. You might have to retune a little, change the volume, etc. The schematic is over here. And this is worth looking at because some of this is going to be used in this Q-enhanced filter technology I'm going to promote at the end. I'm going to use a different variant when we do the Q-enhanced filter, but let's look at this one. The antenna comes in right here. And there's a potentiometer which allows you to do gain control. It's not automatic gain control, but it's manual gain control. And then it goes through, what's this? It's a common gate amplifier. And there's an LC tuned filter here, which consists of these capacitors in parallel with whatever inductor selection you do to go to the different bands. So the signal gets bigger from here to here, and it's selected somewhat by the LC tuned circuit. And then it comes over to this device, which we're going to view as a common drain amplifier in the sense that the signal that comes into the gate comes out on the source, and then look where it goes. It goes through a potentiometer, but then it goes into this common gate amp, which looks just like this one, and then it comes back into here. So there's a feedback loop here, which is a positive feedback, and that does what we said earlier. It increases the gain through what's called regeneration, and at the same time it sharpens up the filter. But the main technique is this: filter, amplify, feedback. The problem with all of these architectures, including this regenerative one, is the filter bandpass shape is still not good enough. And so we got away from this back in the 1930s and went to super heterodyne receivers. So here are 4 super het designs. The one on the top left is basically what we used in Radio Design 101, except we did not implement the AGC. In this design, the preselect filter and the image filter together pre-select just the FM broadcast band and try to block everything else. So the entire FM broadcast band hits the mixer and gets mixed down and then finally filtered to select a single channel. But if you've got strong signals, then they can create intermods anywhere along the way prior to the IF filter, prior to where you strip out only the single signal you want. So a solution to that is shown in the top right. Here, the difference is there's a filter tuning control that changes the frequency of these 2 filters flanking the LNA. And so you can make these filters sharper than the 20 megahertz wide FM broadcast band. These filters could be made, say, 4 or 5 megahertz wide, or ideally 200 kilohertz, which is what we're going to do in our design at the end. But with normal components, you can't do that. And so a practical limit is maybe 4 megahertz wide. But you would have to tune them as you retune the LO to dial in a new station. A couple of other alternatives are shown at the bottom. At the bottom left is a multiple conversion super het. This is what's used in the VR120. It's also used in a slightly different form in the spectrum analyzer that I was using. In the VR120, there is some pre-selection filtering and amplification, and then mixing, but the mixing is to mix up to a higher frequency where there's a narrow filter. In this case, they use a surface acoustic wave filter, and then some more amplification and or mixing, and that then mixes it down to a lower frequency like our 10.7 megahertz, where the final channel selection is done. And finally, over here on the lower right is an architecture that came out when people were trying to integrate receivers. They didn't like filters, and so they said, hey, let's take the antenna and run it into an amplifier and then mix it down to a lower frequency. And if we do this right, maybe we use something called an image reject mixer, we can solve the image problem, and maybe we can make this work. And we'll take a look at this. This is kind of what's used in the ATS-25. So I've got examples of each of these 4, and let's walk through them. The first one is our super het architecture that we did in Radio Design 101. So I'm not going to go through this. You can see the frequencies involved here. The IF filter was at 10.7 megahertz. We used a fixed tune pre-select image filter combination, and that led to problems, like we've mentioned. This is the SW60 radio and its front-end schematic. If we set it to the FM broadcast band, this switch would go to here, connecting the antenna to L1. And then this set of 4 components is actually a 2-pole bandpass filter. So that's our pre-select filter. Then we go into a common base amplifier, and we have a single pole image filter at the output. But look, that filter is tuned. This little dotted line means that there's another capacitor which varies at the same time, and that's the capacitor that changes the local oscillator frequency. So when the receiver is tuned by changing the local oscillator frequency, we're tuning, in this case, just the second filter at the same time. In the SW60, this is a fixed tuned filter. But this image filter is quite narrow. So I wanted to see how narrow it is. And to do that, I took this thing apart and tapped into some of the circuitry, and I'll show you the results. Of course, before I do that, I'm going to mention there is this caution on the back of the radio, and you have risk of electric shock. Don't open this, but it says refer servicing to qualified service personnel. Well, I think I can do that, and actually worked in a TV shop when I was younger. But you know, I've also done electrical engineering, so there is some AC in here, so you have to be a little careful. But the radio itself runs on about 6 volts. Now, the schematic that I showed you, I finally found the parts on the circuit board. This is a 1-layer circuit board with traces on the back side, and you can see the components here on the front side. Fortunately, they're labeled, and L1 is where we came into the pre-select filter, and then this is the low noise amplifier transistor. This is the mixer. And then what I did is I figured out where to tap into the output of the low noise amplifier. And you can see I've soldered a lead on right here. The output of the amplifier is right here. This is my resistor that I added. This is an 810 ohm resistor because I didn't want to load this node too much. So this node is loaded with about 1K ohm when I'm measuring. Why 1K? Well, this is 900-ish ohms, and then looking back into this cable, which goes to the vector network analyzer, there's a 50 ohm, and so it's 950. Anyway, it's a K ohm. And this is the ground point that I could find. And then I set up the Nano VNA to measure the filter shape. I'm actually going through a step attenuator so that I can make sure that I'm not overdriving that low noise amplifier, because that would distort the shape. And so I'll skip all the details of that, but you need to do that when you're measuring an amplifier's response. Here's the response that I measured when we're tuned to around 98 megahertz, the center of the band. The gain is 1.46 dB, but I had 20 dB of attenuation in during this measurement, so it's actually about 21 dB of gain. Each division is 20 megahertz, so the filter bandwidth at 3 dB down is about here, and it's about 4 megahertz. So that's a selectivity Q of 25. And this is the reason that it can't be made much more narrow, because remember, this is made out of an L and a C, and those components themselves have a quality factor limitation, and so you're not going to get Qs of higher than about maybe 50 at the very most. And in this particular radio, apparently it's 25. Another limitation is how well it's going to track when you change the LO. So what good is it? What does it do? Well, hopefully this illustrates that to some extent. I've got 3 panels here. On the left is the radio tuned to 88 megahertz. What I'm trying to capture in this screen is what the effect is on the spectrum that we're receiving. I've got the tiny SA hooked to the output of that LNA now, and this is that 96.3 station that's quite strong in the area. We're tuned to 88 megahertz, so if we look down here at the low end of the band, we can actually see a couple of those stations that we listened to earlier on in this video. If we retune to 98 megahertz, now look, that signal, which was at this level, is now about 14 dB higher. If we look at the far right, that's where we've tuned to 108 megahertz, and so the filter's centered up there, and now these signals at the top end are really pulled out of the noise. And the signal at 96.3, it is sufficiently far away that it's suppressed. It was here when we were tuned to 98, and now it's down here. So the ratio of how big that is to how big these are is much better. And so we're going to be able to receive these okay. And that's the purpose of this architecture, which is called a tracking pre-select filter superheterodyne design. Whew, that was a lot. All right, let's go on to the next one. What's the issue with the VR120? Well, remember in that we mix up to a higher frequency and then we mix back down. And anywhere along the way we can generate intermods, especially if there's too much gain. So like the SW60, this is a multi-band radio. This is from a manual I found online, and you can see the block diagram. The antennas here, they do have an attenuator that you can turn on and off. And depending on what frequencies you're trying to receive, you go through one of several pre-select filters. And then the low noise amplifier. So the pre-select filter we're going to go through is this one for the FM broadcast band. It'll also let shortwave through. Fortunately, with a reasonable size whip antenna, there's not going to be a lot of power in the shortwave signals coming in. So that's probably okay. However, we're going to look at this amplifier and this mixer and their compression point and that sort of thing. This is that first filter at the higher frequency. It's 248 megahertz. And then we mix down to 15 megahertz in this case, and then amplify more, and then go into even more amplification and demod. Here is the associated schematic. And before we get into it, let's look at that first filter. The guaranteed attenuation at F0 plus or minus 0.6 megahertz is 25 dB. And at plus or minus 1.2 megahertz, it is 40 dB. So this is not a real sharp filter with real good out-of-band rejection, but it's not bad. The signal comes in over here on the left, and it goes through some switching, and this is basically attenuation. The signal after the attenuation goes this way, and depending on which band, one of these diodes is turned on as a switch and lets the signal through. So we're following this red line. This looks to me like a 5-pole elliptical low-pass filter. Remember, this is like 0.1 megahertz up to 110 megahertz. So they're basically just low-pass filtering with a little AC coupling along the way to get that. And then here's a switch at the output so that we're not also connected to this filter and ones below it. And so the signal then doesn't go this way, it goes on down following this red line. And where does it go? It goes into these two transistors, which is a cascode amplifier. Cascode amplifiers, I don't know what the gain is here, but they tend to have gains of 20, 30, or 40 dB. Then it comes up here to this mixer chip, and I pulled the data sheet for this. This seems to have an input referred compression point somewhere around minus 20 dBm. So remember, if you got 30 dB gain ahead of that and you got a minus 20 dBm input compression point here, then the antenna referred input compression point is going to be minus 50. And that's why they give you an attenuator, because you're probably going to have to turn that on. Otherwise, you're just going to be hitting the heck out of this mixer. Anyway, after that mixer, it goes through that filter we mentioned, which may or may not block all the signals that you want blocked because it doesn't have that good of out-of-band rejection. And then it goes through another mixer, and then finally this filter. And after that, it's free game to amplify as much as you want. But before that, anywhere you could get intermods. Now, in this document, we also looked at the ultra-low IF, talked about it, as well as designs with image reject mixers, which most of these are going to have these days, or maybe something called selective demodulators, but that's not really a thing. The next in line is the direct conversion receiver. And the ATS-25, which seems to work quite well, uses essentially a direct conversion receiver architecture, although they call it a low IF architecture. Let's take a look at that. So here is that cool radio, and very nice display. This is what's inside it. There's not a lot inside it. In fact, the entire receiver is this chip. These other chips are a headphone amplifier and a speaker amplifier, I think is what these two are, and then a battery control chip over here. There's also some stuff behind the display for controlling all of this, a microprocessor. But to look inside this chip requires a couple of things. Number one, you need to pull the data sheet for it. So I've done that. This is the SI4732 is what's used in the radio that I bought. And here's the block diagram. In FM mode, we come directly into a low noise amplifier. And there is no filtering as far as I can tell. In fact, I'm pretty sure there's no filtering on the way into this low noise amplifier. Now, ordinarily, that's going to be a big problem because you could have some out-of-band signals that are very strong. However, in most environments, the FM broadcast band are some of the strongest signals that you're going to receive. And if your antenna is a reasonable length, like 30 inches or 75 centimeters, then things like shortwave stations aren't going to pick up well. And the main things that the LNA is going to see is the FM broadcast band. But that still means that you're going to have that wide range of signal levels for all the different channels in the FM band. And I fully expected this radio to have issues. It does have a few, but they've done some really clever things to make this thing work well. Two of those things are to use AGC and to use what is called IQ mixing. And in the signal processing, they can then take that and create image reject filtering. They do that in the digital signal processing part of the chip. They also do the demodulation here, and then they go out through some digital analog converters if you happen to want an analog signal coming out. You can also get a digital signal coming out to an SPI bus. Now, this is a multi-band radio, so in addition to FM, it can receive AM broadcast, as well as long wave, medium wave, and short wave. And that's where you run into a little bit more of a problem with not having filtering on the way in, especially in the ATS-25 where they do not have all of this. Instead, the antenna connector just goes directly to this LNA in this bottom section. And I have noticed cases of the FM station at 96.3 preventing me from getting certain shortwave frequencies. Now, to dig deeper into what's going on inside this chip, I looked at the different chip variants that they have and identified some patents that were referred to in the data sheets for those, and this is one of those patents. I'm not going to go into this one in any detail because it doesn't show a whole lot more than what I've already said. They do have variable gain amplifiers at the output of those IQ mixers. So that's the main thing I got out of this. These are some of the things that are in the digital signal processing circuitry. Here is another associated patent, and I think this is probably telling us a lot about why that radio is working well, even without any filtering on the FM broadcast band. I think a lot of the performance success has to do with very judicious use of the RF attenuator before the LNA and varying the LNA gain for reasons I mentioned earlier. They do that by looking at, apparently, the output of the LNA through, I think this probably stands for peak detector. I have not read the patent in detail. So they're able to sense when the output of the LNA is getting close to saturation or getting close to the point where the mixer would saturate. And when that happens, they can go into the processor and dial back the gain in the LNA and or throw in attenuation. And similarly, they can do the same thing with the variable gain amplifiers in the baseband portion here after the mix down. So, in lieu of filters, we have a lot of control of gain. And it's fun to get this radio and to mess around with it and kind of see how this is working. There is a AGC that you can turn on and off by touching. It's a touch screen, so you can touch this, turn it on and off. You can go to this next menu and you can actually vary the attenuation manually. So here's a demo of how all that seems to be working. I'm going to let you listen to the radio being tuned to 98.5. Now 98.5 is this little tiny station right here. And just to the left of it, 2 megahertz away, is our super strong interferer. So this is 70 dB down, only 2 megahertz away. Let's listen to how well this radio is able to deal with that and see if we can understand how the AGC seems to be playing into that solution. So this is pretty impressive. This is 98.5, which is about there on the screen, and it's not even above the noise floor on the spectrum analyzer. And this little ATS-25 is picking it up. Now, I did have to go into the manual attenuation settings by hitting this next button and setting the attenuator at 16 dB. If I use it in the normal AGC mode, so you can't hear it very well there, let me change it to manual attenuation. Yep. See, now you can hear it. Now, if I turn the attenuation down we're going to get a lot of other distorted stations, spurious responses that shouldn't be there. So we got 16 dB, 12.
Relocating somewhere new is an adventure, but it's also a lot of work. There are what look like high-voltage.
So that's not supposed to be there. I don't know what that is. That's two different stations on top of each other, and it's not supposed to be there. If we go back to 15, this really helps to demonstrate the beauty of using attenuators to deal with the very strong stations. And remember, this guy is right here, and this guy is up here, about almost 80 dB bigger. All right, let's summarize some of the key points that we've demonstrated here. And then we'll finish off with a quick look at this ideal low power receiver design that we're trying to add to our Radio Design 101 receiver using Q-enhanced filtering. So here's the key takeaways from what we've just seen. Number one, strong signal interferers will create blocking and intermod problems in receivers, especially if those receivers are designed to be operated on low power. And those interferers can be out-of-band interferers or in-band. The FM broadcast band provided an excellent demonstration of this. It has stations that vary drastically in amplitude by 70 dB or more. Now, the traditional solutions to dealing with these problems started with pre-select filtering and image filtering. And very early on, those were augmented by gain control and automatic gain control in receiver designs. These solutions date back almost 100 years. While not directly recognized in the architecture block diagrams shown, selective antennas also play into this. If you're a radio amateur, you probably know that. You have a resonant antenna. It works better at your frequency than other frequencies, so that provides a little bit of bandpass filtering. Or your antenna might be directive. You might have a beam antenna to focus the energy in one direction and block signals coming in to your receiver from another direction. But directivity can also be played with simple dipoles, where you move the antenna around and position it where it gets in kind of a null of the signal that's interfering with you and not in a null of the signal you're trying to receive. So you can select that way. But finally, higher power consumption is a really good way, because that can improve the compression point and the intermodulation performance as well. That's what spectrum analyzers do. They do that, and they generally have attenuators at the front end. Now, of all of these methods, if you're looking for good low power performance where your receiver isn't draining your battery too much, then doing tracking front-end pre-select filter is probably one of the best approaches, combined with the others. But traditionally, that's been difficult to do, to get a bandwidth, say in the FM band, more narrow than 3, 4, or 5 megahertz. However, we could leverage this classic technique of regeneration, which, remember, that sharpens up filter responses in addition to increasing gain at that one particular frequency. And in the modern world, that's in a research area called Q-enhanced filtering. That offers us the possibility of getting very good performance with very low power consumption. And that's what I'm considering the ideal low power receiver. So here's a block diagram. This is from that document I wrote long, long ago. This is the ideal case. So in the ideal case, you can do anything you want. So let's assume that we can create a pre-select filter which is very narrow and selects only the channel we want, and we stick that right at the antenna. Well, we would have to tune it when we retune the receiver. Okay, well, that's a problem, but maybe we can solve it. In addition to that, there could be very strong signals around that you want to receive every once in a while, so you might want an attenuator out in front of that. The rest of the receiver, remember, after we select the single channel we want, intermods don't matter. And so we can then amplify the heck out of it. We could filter it some more. We could mix it down to another frequency. And these active elements, the amplifier and mixer, aren't going to create intermods that are going to hurt us because there aren't going to be any other stations to mix with. So we can do whatever we want for amplify, and we can do that at low power and the demod. But the trick is this pre-select filter, getting it sharp and having it work directly at the RF frequency. So I'm going to leave us with a challenge. This is a prototype Q-enhanced low noise amplifier / filter circuit, and this was previewed in the last epilogue 2 of this series. It substitutes for the low noise amplifier we originally built in the Radio Design 101 receiver. It has 2 controls. One control, this one up here, controls the frequency. There's a varactor diode in this circuit. In addition, there's another control that controls the positive feedback, and what that does is it sharpens up the filter and increases the gain. And if you get them both set right, and let's say you want to tune to 89.7 megahertz or whatever this frequency is right here, and you crank up the regeneration just the right amount, you can have a very strong amplification of close to 30 dB. And you can have a bandwidth which is only like 200 kilohertz wide. And through these controls, you can vary the frequency. That's this arrow here moving left and right. We can also increase it and decrease it by changing the regeneration control. And that changes the gain of the LNA, but the other one changes the frequency of this filtering. Officially, there's only one frequency control, but as we'll see in the next slide, these two kind of go together. The effect of this filter can be shown over here. Here the filter is tuned to 96.3 megahertz, which is the strong station, but we've cranked back the regeneration so that the gain is not too high. So this signal is already strong, it's fine. Anyway, we didn't need much amplification. But let's say we want to receive signals down at the low end of the dial. Well, we can retune the frequency of the filter, and because the signals down here are weak, we can crank up the regeneration / gain, at the same time narrow the filter up. So that's what was done in this lower plot, where we centered the thing at 89.5 megahertz. We enhanced the Q to about 500, i.e. made a 200 kilohertz wide bandwidth, and it pulled all of these stations out of the noise and made them very receivable. At the same time, it actually decreased the amplitude of the strong interferer here by about 10 dB. So we pulled these up by about 30 and decreased that one by about 10. So we did have a signal to interference ratio of about 50 dB, but now we've decreased that to 10 or 15 dB. And that makes the receiver's job from that point forward much, much easier. It's not the ideal filter, but it's pretty good. And right now it only tunes on the lower end of the dial due to the varactor tuning range. So I wasn't able to test it across all frequencies, but all the frequencies down here at the low end that I was able to test it on, it receives perfectly well, including the very weak 88.1. These higher frequencies are to be determined, but it should work up there as well. And here's a high-level schematic of that filter without the details of the varactor tuning control. The design is built around a simple common base amplifier, transistor Q3, with input here on the emitter. The source is shown over here on the left, and I've originally designed this for a 500 ohm source impedance. That could be a 50 ohm where you've got a Q of 3 matching network to bump it up. DC block, signal comes into the emitter and out on the collector, standard tuned RF amplifier design where we can change the frequency here. Again, with a varactor diode, or there are some digitally tuned capacitors you can buy now, which are kind of cool. And then buffered with a common collector stage Q4. The emitter becomes the output, but that output is fed back to the input through this path. And that's where the regeneration takes place, and that can be controlled with pot R4. I think I implemented this in that previous layout with a 1K pot. So it's adjusted to about mid-range. Since it's an amplifier, there's got to be attenuation, so there's a 50 ohm resistor here. And so we can adjust this to control the amount of feedback. We want it to be a little bit less than unity feedback. And when we get that, we get a response something like over here on the right, if you get everything adjusted right. So that's the trick in these things, is you've got to have some kind of an automatic tuning control in practice. But if you get it adjusted right, then the gain can be like 30 dB, and the passband is very narrow, so you could have a Q of 100 to 500 or something. And then at other frequencies, say down here at 88 megahertz, when we're tuned to 98 megahertz, instead of having a gain of 30 dB, we have -3, Conversely, we could retune this so that it's centered at this lower frequency, say 88.1, and we have 30 dB of gain there and minus 3 dB at 98 megahertz, which is roughly where our strong signal was. So that's great, but it even gets better. Compression can actually occur either at the output of this amplifier or at the input. And so what we'd like to have happen is when the signals come in, if they're not at the center frequency, we'd like them to be attenuated. And this design does that. As you can see on the lower right, the response to VN is actually close to minus 20 dB when you're off frequency by 10 megahertz. So you get attenuated by 20 dB coming into this thing. So that should prevent nonlinearities and intermods generated at this emitter to base node, which to some extent could decrease the need for attenuation and AGC in this thing. So that'd be cool. So it's still under development. Further development of this thing hopefully will take place, including linearizing the amplifier and doing the tuning control algorithm. But that's not going to be in the Radio Design 101 series. We're done with the Radio Design 101 series after this video. However, we might do some future videos, but they'll be called something else. And some of the things we might look at are performance measures. Compression points we've already met. Look at this intermod thing more. There's something called the third order intercept point that we haven't talked about, but you can Google that and look for YouTube videos on it. There's some good ones out there. And how these things play against the power consumption. Then there's also an issue of spurious frequency products from mixers. The intermod's probably the biggest one there, but many of you know there are issues like images in a superhet design. So that would be a spurious frequency response. There are actually things called half IF spurs and I think third IF spurs. Anyway, so mixers can create problems in addition to the ones we've talked about. But I think we've captured the main ones here. Ideal sensitivity of a receiver. Assuming you don't have any strong signals at all, how weak a signal can you get? But that's becoming less important, as we mentioned in a previous video these days, because there are elevated noise floors in a lot of environments. And it's caused by lighting or by power supplies in electronic devices. They have switch mode power supplies, and that's raising the noise floor in a lot of locations. So I don't know that noise figure matters that much anymore, unless you're doing like a satellite receiver or something at very high frequencies. Okay, that's it. I know it's a long video. I hope you stay with me at this point. If you're hearing me, I know you did, or you skipped ahead. And so I thank you very much for watching. I hope this has been helpful to you. And if you haven't seen the whole Radio Design 101 series and you're interested, go back and look at that. I've also got some videos on nano VNAs. But hopefully in the future we might cover some of these other topics or more. Thank you for watching.